Hi everyone, I'm Hussam Abbas. I'm an assistant professor in electrical engineering and computer science at Oregon State, although I work 3 blocks down the road because I live in Portland. This here is my student, PhD student, Colin Shea Blymyer. Colin got his master's in computer science from Virginia Tech, working on automated scientific discovery, and joined OSU as a PhD student in the fall of 2019. So we got to have a few meetings in person before everything shut down. And this we'll be presenting sort of a summary of the work he's been doing for the last few years at Oregon State on the formal verification and elicitation of ethical obligations from autonomous systems. And with that, Colin.
Hello, my name is Colin Shea Blymyer, as you just heard. I'm a PhD student advised by Hussam Abbas at Oregon State, and I'll be introducing our work on generating Deontic obligations from utility maximizing systems and other sorts of automata as well. In 2016, Mercedes decided they solved the trolley problem for self-driving cars. They announced that their cars would sacrifice pedestrians in order to save passengers. A week later, they recanted, saying there is no instance in which they made a decision in favor of vehicle occupants. Made explicitly, can these same ethics be implicit in the system? In January of this year, Tesla released an update for their autopilot services that allowed their vehicles to roll through stop signs. In February of this year, they removed that feature after 2 meetings with the US National Highway Safety and Traffic Administration. These news stories show how important it is that the ethical decisions made by self-driving cars really are, and how important it is that their social obligations are communicated to the communities that host these vehicles. And it's not just self-driving cars, it's autonomous delivery drones and robots in hospitals and nursing care. Given an embodied system like one of these, how can we learn what social and ethical obligations these systems have? And can we express these obligations in a human legible form? A self-driving vehicle is composed of many control loops: steering, acceleration, localization, object detection. And we know its mission is to go from point A to point B, but we want to know what its global obligations are. For example, can we determine if the car is potentially obliged to sacrifice pedestrians in order to save passengers? And can we express that obligation in a human readable form? Sometimes these obligations are programmed in, like Mercedes had planned to do. But often the complexity of such systems obfuscates their obligations or leads to obligations that emerge from their control loops. How then can we get guarantees about the ethical norms of a complicated robotic system? We use formal methods to prove that a system has a given obligation, and we express these norms in a human readable logic of obligations. Most formal methods use alethic logic to check for forbidden behaviors. But what if that behavior occurs anyway? For example, we might have car A following car B, as in this image. Let's see if I can, there we go. And we might ask if it should pass on the left. Since we can see oncoming traffic, we want to specify it should not pass on the left. But if car A hits a slippery patch of road and swerved into the left lane, what should it do then? We want some way to formalize these sorts of specifications, these obligations, what the car ought to do and what it ought not to do, and draw logical consequences from them and do all sorts of other sort of formal verificational tasks with them. So you might imagine doing this with a specification logic like computation tree logic or linear temporal logic. I'm going to explore that a little bit. So these alethic logics, logics of necessity and possibility, are the most common for specification of behaviors. And here I've given the specification, the car should never speed. In alethic logic, common ways of writing that. However, if all norms are expressed in necessity, as this one has been, then it's never possible to actually violate that norm. Despite the fact that norms can generally be violated. I sped on my way here to Portland today. Maybe I shouldn't have, but I did. And so it'd be unfair to say it's impossible. There's no accessible world in which I didn't speed on my way here today. Instead, we have to find some formalism to say, I shouldn't have done that. So if the car is forced to speed, as would happen if a part breaks or it hits an icy patch on the downhill, then the specification in alethic logic becomes incoherent. Further, the injunction against speeding implies that obeying the speed limit is compatible with the realization of its other objectives. There's something extra to an obligation that says something about the compatibility of the specification with what else the system is trying to do. Whereas with an alethic logic, when you say it cannot speed, you're saying nothing about what its obligations, what its goals are, what its objectives are, its tactics. You're just saying this is impossible in the system. So it seems like, to me anyway, and to my research, that alethic logic is insufficient to express these sorts of norms. So we're going to turn to Deontic logic. Deontic logic specifies obligations and permissions. In our work, we use versions of Dominance Act Utilitarian Deontic logic, invented by American philosopher John Horty. To specify an obligation in our Deontic logic, we start with just an atomic proposition, don't speed. If we want to know that our self-driving car will break the speed limit, then we start with something like this. Because our system operates over time, we add a temporal modality to ensure that there's no point in the future in which the vehicle speeds. So we say, always don't speed. The vehicle never speeds. To model the agent's ability to choose its actions, we include an agency modality. Now we can say the agent sees to it that something occurs. The agent sees to it that it never speeds. Finally, we have an obligation giving us, by acting optimally, the agent ensures some facts about the world. And by acting optimally, we mean it takes actions whose outcomes dominate the outcomes of other actions. And I'll get into that in a moment. And this is Horty's logic, Dominance Act Utilitarianism. So this is what I mean when I say an action is optimal if its outcomes dominate the outcomes of another action. We see here the formal model that DAU, Dominance Act Utilitarianism, is defined on. It's a branching tree, and each history is labeled with atomic propositions, A or speed or don't speed, and values as well, 10, 9, 3, and 1. That's how good, in a sense, these histories are. And so we can say stay in lane, in this case, is the optimal action, because 10 and 9 dominate the set of values for the histories from changing lanes, 3 and 1. 10 and 9, the set 10, 9 dominates the set 3, 1. So stay in lane is optimal in this sense. So what can we do with deontic logic? We can prove the consequences of a set of obligations. We can check if a robot or a system follows a given ethical rule or obligation. We can determine obligations from human preferences on a system's behavior, and we can explore what obligations a robot has learned to follow. With deontic logic, we can prove the consequences of adopting a set of obligations. For example, Intel made rules for self-driving cars called responsibility sensitive safety. They express these rules as mathematical formulas, and these equations give rise to vehicle behavior. So how can we abstract away from these formulas to reason about ethical consequences in the system? We translated those rules into deontic logic, and we proved that they had an unexpected consequence. Because RSS states that a car doesn't need to consider how it might influence interaction between two other cars, These rules permit a vehicle to facilitate a collision between two other vehicles, which is pretty unfortunate, to say the least. We also developed a model checking algorithm to verify whether a weighted automaton has a given obligation. There's an example here of such an automaton. The transitions are weighted according to a weighting function. So the value of a history or an execution of the automaton is an aggregate function of the weights that we place or are learned by some reinforcement learning procedure that are placed on the paths that are identified with the history. So given such an automaton in a formula in that logic that we've adopted from John Horty, we can determine if the automaton has that obligation. This is different, of course, from determining if the automaton executes that obligation. The automaton might not do what it ought to do, but it would still have that obligation. This is what makes really something like DAU and Deontic logic different than Alethic logic. An agent would never be able to deny a formula, a specification that is true in the system in Alethic logic, but in Deontic logic, we can just say it prefers to do this, but it's possible to do other things. And now we could reason about and check for obligations. We started to think about how to democratize the selection of obligations. One of the weaknesses of the formal approach so far is that the obligations that will be checked are selected by a system designer or auditor, potentially a small group of people who have their own way of viewing the system. We wanted a method that allows us to engage an entire stakeholder population. And learn what from that stakeholder population they would want to see enforced or engaged as obligations in a system. So to do this, to learn obligations from the preferences of a population, we start with an unweighted automaton as a model of potential system behaviors. We then sample pairs of behavior from the automaton. Here, behavior A shows the ego vehicle, the red one, tailgating, while behavior B shows the ego vehicle maintaining a safe distance. Then we show these pairs of behaviors to a population. They choose which behavior in each pair that they prefer, and from the statistics of which pairs are preferred, we can infer weights on. And from a weighted automaton, we can start to infer the obligations that are implicit in the population's preferences. But that's an area of future work to really get from that weighted automaton to here are the important obligations that the population wants to incur. So we did some experiments with these methods with a bunch of different ways of taking pairwise comparisons of behavior and turning them into weights on automaton. So the blue line that sort of starts at the top and then goes down low, it has pretty good errors on the y-axis. Label disappeared at some point. Whereas on the x-axis, we have essentially the number of comparisons that are being made by people. So the more comparisons people make, most of the other systems pretty much stay constant, which is not great considering that the blue line is the best you can do, essentially, and the red line is a Bradley-Terry comparison, which is sort of like an ALOS score for chess rankings, except instead of ranking competitors in a chess match, we're ranking the preferences of a population on the performance of certain behaviors of the system. And that Bradley-Terry method turned out to do pretty well. So we have a method for turning the preferences of a population, at least into control, and hopefully in the future into a set of obligations that we can identify. We have methods for model checking in automata. We wanted to explore auditing and explaining the ethics of robotic systems to Markov decision processes, or MDPs. MDPs make up a pretty broad class of models of environments and systems in especially reinforcement learning. And we hope to make our research more applicable by expanding it into that area. So a Markov decision process models, if you don't know, an agent's non-deterministic capability to choose from actions in a stochastic process. These models are core to many reinforcement learning algorithms, and they are defined as a set of states the agent can be in. Here we have states 0 through 19. Actions the agent can take. In this example, up, down, left, and right is what we would call a grid world. Probabilities that an agent moves from one state to another after taking an action, say the action you choose always has a 70% chance of actually happening, and you got a 30% chance of randomly taking one of the other actions. Rewards that the agent receives when entering a state. So in this case, the agent gets a little penalty for not reaching the goal state, which is over at 14. It gets plus 10 points when it gets to state 14, and gets minus 10 if it enters any of the red states. And then a discount factor that makes future rewards less valuable. This is important for the aggregation of rewards over time. And then finally, we add propositional labels to the states, like the red states being bad or negative. We have perhaps a red labeling on there. And so we can say things like it has an obligation to never enter a red state. In reinforcement learning, the agent learns what the appropriate rewards are on each state. So if the car we are evaluating could be modeled as a Markov decision process, then we want to know what are the consequences of taking actions that maximize the rewards the agent has learned. If we're given an agent that has learned its policy, we might want an answer to a question like, does the agent have an obligation to enter a red state more than 20% of the time? Given this MDP and this obligation, how can we learn whether the agent obeys it? Of course, we can use formal methods, but before we turn to those, we can think of some other approaches we might take. One way is to do this sort of statistically. We might assume that the results of actions are usually what the agent intended. And by looking at a large number of executions from the Markov decision process, we could determine patterns of behavior that we might be tempted to call its obligations. However, we wouldn't know when a trajectory was intended or just unlucky. And further, our ability to collect this information diminishes greatly as the complexity of the process increases. At that point, the sample complexity becomes pretty difficult to overcome. Alternatively, we could manually inspect the reward function that the agent has learned. And this might tell us if the agent would choose to enter some state. It doesn't tell us about the relationship between some states, such as don't enter state 5 until you pass through state 7, or you can enter state 15 eventually, just not right now. So if we're not satisfied with those techniques, we propose using Deontic logic to express these obligations and formal methods to prove that a system satisfies these obligations. However, because this is a stochastic system, and so far we have only been working with finite state automata, non-deterministic logic or modified logic, to be able to express obligations in such systems like these. So our approach requires a model of the system, a Markov decision process, a language to specify normative behavior in stochastic systems, our new Deontic logic, and an algorithm to check if a system has that behavior, which I'll introduce in a little bit. So our new Deontic logic, expected act utilitarianism, makes two changes to Horty's dominance act utilitarianism. It includes a probabilistic modality that P with the greater than 0.9 in this case. This probabilistic modality accounts for the stochastic dynamics in the environment. And we change the notion of acting optimally from Horty's almost game theoretic accounts of optimal actions to Bellman optimality condition. So we're just trying to maximize, the optimal action is the action that maximizes the agent's expected utility. So we have obligations in the form by acting optimally, the agent ensures some facts about the world, and by acting optimally, highest expected utility. We arrived at expected act utilitarianism, the logic we use for Markov decision processes and their obligations. To review, EAU, expected act utilitarianism, describes the obligations of agents in Markov decision processes. This allows us to specify normative behavior in a large class of reinforcement learning models. This formula this formula up here, alpha C stit A, says the agent alpha has an obligation to see to it that A is the case. An obligation is just the state of affairs, A, that is guaranteed by taking Bellman optimal actions. And in this case, the state of affairs is defined in terms of a probabilistic logic. We can use EAU to say something like, the agent ought to ensure that it reaches state 0 on the second step less than 20% of the time, as I've put down here at the bottom. If entering state 0 is unsafe or illegal or otherwise morally significant, then this obligation specifies an ethical norm, and we would like to know if our agent follows it. That is, how can we prove that an MDP satisfies the specification? Well, we devised a model checking algorithm to prove that an MDP satisfies an obligation, and it's available at this GitHub repository publicly. It takes in a Markov decision process and a formula in EAU. It decides if the MDP satisfies the formula and determines if the agent obeys the obligation or has the obligation, if that is what it would prefer to have. I'd be happy to answer more questions about the specifics of our model checking algorithm offline or at the end of the presentation. However, we still have a problem. Which obligations should we check? Should we check all the obligations that the agent might have? Well, there are more than 100,000 obligations in our logic with fewer than 7 symbols that can be checked. So even very short, like human readable obligations, there are hundreds of thousands of them. And most of those obligations are irrelevant or trivial. The agent has the obligation to not be in 2 states at once. You know, these are not things that we really care to check, but they are there. So doing an exhaustive search of the space of obligations doesn't really seem like something we want to do. Maybe we should just check the obligations we know are important. We come to this system maybe with some preconceptions of what we would like to see the system do, but we might miss important obligations. We don't know what they all are. We don't know what we don't know. So if we have designed a system and it behaves unexpectedly, how can we have expected to ask questions that would have caught that behavior? Instead, we would like to have some procedure that winnows the space of obligations down to just the ones that are interesting to us. For example, if you are interested in the relationship between an autonomous vehicle and pedestrians, then the procedure should learn to formulate statements in EAU that explored the obligations of the vehicle with respect to pedestrians automatically, or as automatically as we can make it. So such a procedure would predict a user's interest in an obligation based on their feedback. Choose a good obligation to test, check to see if it's valid. Then the user could provide feedback, maybe score that obligation, and then the procedure would continue updating. Ideally, it does this with minimal human interaction, but we need some model to predict a user's interest in an obligation or formula. So how do we do that? How do we check an obligation's validity? And how do we generate obligations from our model of the user's interest? We propose a Bayesian optimization procedure that uses a Gaussian process to predict a user's interest in an obligation. We check for validity with the model checking algorithm that we introduced. And to generate obligations, we use a genetic algorithm that has at times an annealing rate to get it to focus on actually valid obligations instead of just obligations that are syntactically sound but aren't true given the model that we have, given the system. So to determine if our procedure for generating interesting obligations was effective, we performed a small pilot study with 4 subjects who were familiar with Markov decision processes. We introduced this cliff world that I've described already. The agent trying to get from state S, the state label with an S, to the state label with a G quickly while avoiding the red state. And the subjects were asked to take the role of a system designer who would determine how interesting some obligations were about this Markov decision process. The obligations were translated into English by myself, so the evaluators didn't need to know the probabilistic logic or the Deontic logic. Each subject started by seeding the Gaussian process with 10 random formulas and how interesting they thought they were on a scale from 1 to 100. Then they performed 20 updates of the model. So it would come up with an obligation, say, how interesting is this to you? And you say, oh, it's a 77. It's got a state in there that I'm interested in, whether or not the agent reaches or some sequence of state transitions that the evaluator thinks is neat. And then the model would update itself based on that behavior. And finally, the subject judged 10 randomly generated formulas and 10 formulas that the Gaussian process with the genetic algorithm produced. So an even mix of randomly generated formulas with formulas that were optimized by our procedure to determine how well we performed versus random. And then we compare the performance of the random formulas and the optimized formulas. So before showing some quantitative results, I'd like to share some examples of obligations that were generated randomly and by our Bayesian optimization procedure. This randomly generated obligation is for the agent to ensure that the probability isn't high for something impossible. This name equals 13 until name equals 0. That can never happen. Name equals 13 can't even be reached. It's in that black box on the right. It's unreachable. This is an impossible obligation. So this is an impossible thing to happen. So for the probability, to ensure that the probability is low, that something impossible has happened, well, it's trivial for anything to do. Then here are some obligations generated by our procedure. This first one is an obligation for the agent to ensure that the probability of reaching the goal state isn't too low. This is the result of one of our human subjects expressing particular interest in obligations that reference the goal state and failure states. So they were most interested in safety properties, essentially, of can I reach state 14 or do I avoid state 0? And then this obligation was for the agent to ensure that it has a high probability of reaching the state above the starting state. So that's state 15. Moving up meant that it had learned, the agent had learned that this upper path was the safer path for it to travel to the goal state. If it took the lower path, it risked falling into the bad state pretty often. If it took the upper path, it had learned to take the safety path. And so this is the result of a human subject who was interested in obligations that revealed the agent's learned rewards. Together, these obligations show, I think, the tool's ability to adapt to different evaluator objectives. In evaluating the performance of the Gaussian processes predictions, we found slightly mixed results. On this graph, a perfect predictor would have every formula on the diagonal. Random formulas in red tended to be difficult for the model to score. You can see on the bottom left where the evaluator scored a rash of random formulas as a 0 out of 100. The model, the Gaussian process was pretty kind to them, rating them between 0 and 40 for the most part. However, optimized formulas, the ones in black, these are the ones generated by our Gaussian process and genetic algorithm. They almost dominate the random formulas in evaluator score. If we use the interest model as a really simple binary classifier, so if you just do the sort of dumbest way to make a binary classifier out of this, We do find that like if we're trying to score interesting versus interesting, so if we put everything in blue as stuff the model thinks is interesting and stuff is in yellow as things the model thinks is not interesting, then it does pretty well. The model struggles with particulars, but more than 80% of the formulas with this scheme put on top are correctly classified. So it seems to get at least the big picture. A big help to the model is that generally random formulas are uninteresting. We can see here the random formulas in red with just the evaluator score. So this is one axis of the graph I just showed. So many of the random formulas were scored as minimally interesting, whereas optimized formulas averaged, I think, around like a 72 out of 100. Let's see. Actually, no, sorry. Obligations that optimize, I have it in my notes, that's good. Obligations that optimize the Gaussian process had an average score of 66, with random formulas having an average score of 13. So that's a difference in averages of 53 points, which is more than half the range, which I think is a sign that it did pretty okay. So this seems to indicate that obligations generated by our procedure are much more useful than random formulas. And we think that this, together with the previous result, shows that pruning the space of formulas using this procedure greatly improves the system designers or auditors' ability to cover important ethical norms. We have two branches of future work. The first is in control synthesis. So we'd like to be able to take an obligation that should have an O in front of the upside down for all. We would like to be able to take an obligation and turn that into control for an autonomous system, or given a set of obligations, or a set of obligations and a goal. Essentially, we want to be able to use obligations to constrain the learning of an autonomous system. And the second side of things is to take an obligation and be able to explore obligation space in the latent space of a neural network. This is the neurosymbolic approach. Essentially, exploring the space of obligations or formulas in general is very hard because it's a combinatoric problem, right? To find a similar formula for whatever your definition of similar is in your use case, to find a similar formula is a combinatoric search problem. That's really complex, both computationally and sort of schematically. What we are trying to do now is embed the important notions, the important underlying notions of similarity in formulas into a neural space so that we can traverse it approximately, but less complexly. The upside with the neurosymbolic approach is that we can always bring it back down to the real world and do more verification. So that's one of the upsides I really see in using neurosymbolic approaches for search. Because once you find something, you can always model check it again. If you have the time, the computational resources to do that. This brings us to my summary. I've shown how we can use Deontic logic to explore the consequences of a system of obligations, how to check obligations for both autonomous or for both automata and how to get obligations from the human preferences, or at least how to start doing that, and how to explore the space of obligations by using human feedback to focus on areas of interest in that space. Thank you, and I have plenty of time for questions. Anybody have any questions for Colin? All right, I guess we will
call it there. And if anybody wants his contact information, it'll be in the video, or also you can contact me as well. So thanks, everybody.
Thank you for coming.